Hello, guys, and welcome to the Science Cafe. Ooh. So this is year number 7 for those that are counting. Thank you all. You've all made that possible. Just a couple of quick announcements tonight. The next Science Cafe, just so you've got it on your radar, 2 weeks, September 23rd. It will be TJ Siders out of Mechanical Engineering on Rage Against the Von Neumann Machine, 3D Printing, the Future and You. All right. Now, nothing to live up to, of course. No.
You guys should go to that lecture.
Yes, but now they're here. Okay, so tonight we got Professor Todd Eisworth from mathematics talking about infinity and beyond. It's all yours.
Thank you very much. I am going to start out with something very, very easy. And I have a couple of assistants I've recruited. Lovely Isabel, will you come? Can you hold? Lovely Adelaide, will you come? Can you hold these? Okay, and maybe I can pick on somebody. Oscar? This is a Sesame Street question. Are there more apples than oranges, more oranges than apples, or are they the same number? What do you think? And why do you say that they're the same number of apples and oranges? 2 of each. And we can, even Adelaide, even though she doesn't like talking in front of people, she could figure out that they were or that they're the same number just by matching up, right? 1 apple, 1 orange, 1 apple, 1 orange, same number, right? So all we are going to do today is that same counting, except as a mathematician sees it. Now, thank you, girls. You may go enjoy your snacks. Thank you, Oscar. So I want to ask you, see this little bit of counting, what's the mental process that goes on when you're comparing collections of objects to see which one has more? Right? It's something we do all the time, right? When you're, I go back to Sesame Street, when you're given a pile of things, we kind of count them out one by one, right? There were 2 apples, well, I actually have 3 apples and 3 oranges up here. We count them out, 1, 2, 3. We're kind of comparing them to a collection of words that we have. And the amount of the apples I'm holding in my hand matches up with the collections of words 1, 2, and 3. I want to run with that a little bit. I've never really lectured with flip charts before, and I'm a horrible artist, so this may get ugly. Be warned, I will do a lot of hand waving. I want you to imagine a shoe store. Don't know how big it is. Certainly maybe something you can find on Court Street, and it's got pretty tight inventory control, so all the shoes are matched up in pairs. And how do you know that the number of right shoes and the number of left shoes are the same? You do, right? I mean, what's going on? Kind of a function. There's a way of taking a left shoe and associating it with its mate, right? They're the right-hand shoe. And every shoe has its mate. And so there's this kind of activity of matching up objects on one side with another. Think about, I guess, looking around the room. How could we determine if there are more people than chairs, more chairs than people, or if actually the same number of each? Yeah, you say, everybody take a seat. And then you see if there's anybody left over, or if there are empty chairs, or if they are, perfectly filled. That's pretty much how we determine when 2 collections of things have the same size when we're dealing with, run-of-the-mill finite stuff. But I'm not content with being finite. I say, part of the tagline for this lecture is infinity a place. What is it? Well, for me, it's a career choice. So we're gonna talk about it for a bit. I want you to imagine an infinite shoe store. Okay? For those of you my age, we could call it Imelda's. Fewer and fewer laugh at that every year. Let's apply the same sort of logic, right? If you have this infinite shoe store, infinitely many pairs of shoes on infinitely long racks, we still know intuitively that there are the same number of left shoes as there are right shoes, right? I mean, no one would argue with that, I think, because you can, every left shoe matches up with the right shoe. What more do you want? That's how we count. And that's kind of my point, is that this idea of counting by matching makes sense no matter what size of collection we're looking at. We see how it played out there in the shoes. Now, I had maybe at some point, some of the discussion beforehand mentioned something about looking at just the natural numbers going out towards infinity and the even numbers, right? Now, there is a sense where to get from here to here, we kind of throw a lot away, right? It's like, well, we threw half the numbers away. But there's another sense in which these two collections have exactly the same size. And I want you to visualize this in terms of the shoes, right? This is your left shoe, this is your right shoe. There's a matching that goes on between these two collections. So it's kind of strange that you can have something that's clearly half the stuff you started with, but if we apply our logical picture of counting, we end up with exactly the same number in a sense. And there are two ways you can approach this. I guess this kind of paradox of, well, we threw half the stuff away. Why are they the same size? Kind of convinced people for many years that infinity made no sense. You just, you don't want nothing to do with it. I guess there was a kind of a shift in point of view in the 1870s and 1880s where it's like, well, that's not so bad. I mean, the notion of counting does make sense. I wonder what we can figure out about it. And I guess this probably takes us beyond Sesame Street, but I do want to give you a word for the day. You can put that up there for now. Well, maybe not. Word for the day. Red is not going to work for us. It's bijection. A bijection, that's a mathematical word for when there exists this kind of matching between two collections. We say there's a bijection between one and the other. There's a bijection between the natural numbers, 1, 2, 3, 4, 5, 6, etc., and the even numbers. You can associate with every natural number it's double. And that matches up every element in each set. And that's a way of counting, how we know that they have the same size, at least from this point of view. It captures the idea of when two things have the same size. So this would be, there is a matching, and I'll put that in quotes because I'm just using your intuitive picture here, between the two collections that we have under consideration. So when we say that there are 3 apples, in some sense, we're claiming there's a bijection between the apples I have and the words 1, 2, and 3. That's how I know that they're the same number. So I want to look at how this notion of bijection plays out with I guess, some of the infinite objects we deal with in mathematics. And the way I'm going to get at it is through a famous thought experiment. It's called Hilbert's Grand Hotel. And what I want you to visualize, it's a thought experiment, you have to visualize, is an infinite hotel, infinitely many rooms, 1 room for every natural number, okay? So here we go. 1, 2, the doorknob, 3, on down a long hall, okay? And picture that in your head. On a particularly busy night, probably homecoming, we've got the hotel is completely filled, okay? But needs somebody important. I don't know, me. I show up and demand a room in this full hotel. The proprietor looks at me and thinks for a bit and figures out a way for me to actually be squeezed in. How does she do it? How can I fit in? How can things be rearranged so that I fit in? Shifting them by one is exactly right. I can say, folks, I need you to add one to your room number and shift one room down the hall. This doesn't work at the Hometown Inn, but it does work here because there's infinitely much space to shift. And if you shift everybody down by one room, suddenly this room becomes open, and I can squeeze in. That tells you infinity is not like other things. It gets better. What happens if 35 of my relatives show up? How can we get them squeezed into the Hilbert Hotel? Yeah, exactly right. Shift everybody down by 35, open up the first 35 rooms, slot people in. So infinity kind of this hotel can accommodate, even if it's full, we can still accommodate any finite number of guests. But what if an infinite party bus from Mardi Gras shows up? Infinitely long, infinitely many seats. We've got a full hotel. Is there a way that we can make this hotel swallow all these new guests? What do you think? Yeah, wow, how? Yeah? Well, we'll see about that. Oh, well, she said if the number of rooms, if the people that are showing up, it's finite, it will never be full. But I don't know, I'm looking for a simple rule here. Exactly right. That works perfectly, right? You can say, hey, you guys in room in, go to room 2N. And if you think about what happens after that shift, suddenly all the odd-numbered rooms are free. And the people from the infinite Mardi Gras party bus can just sneak into their infinitely many spots. Let's make this worse. It's a bad night. Infinitely many infinite Mardi Gras party buses show up. Actually, I think we're probably in Halloween territory by now. What are you going to do? Any ideas? Any thoughts? Is this going to be possible to accommodate all these revelers in the safety and comfort of the Hilbert Hotel? Are we doomed to sleep in the gutters? Yeah. Yeah. Sure. So let's think. This would be a way to maybe handle 3 Mardi Gras party buses. If you multiplied by 4, then the multiples of 4 would be occupied by the people who were there, and then we could kind of sneak in folks. Now the first bus will take the 1, 5, 9, 13, second bus on down the line. I'm going to claim I need a little bit of mathematics here. One way to make this work is to think about numbering the buses. 1, 2, 3, 4, 5, 6, 7, 8, on down to infinity, and numbering the seats on each bus. Seat 1, 2, 3, 4, 5, 6. We'll start by shifting everybody who's currently in the hotel. Do the doubling thing. Except maybe I want to, instead of doubling, I want to double and add 1 so that I have the old people who are here stuck in the odd-numbered rooms, freeing up the even-numbered rooms. And then, I guess, let's see, bus M, seat N. We'll send them to the room 2 to the M times 3 to the N. It's a room number. Now, this actually works. We're sending, the new folks are all getting stuck into even-numbered rooms, so we should be okay there. All the even-numbered rooms are free. And we're relying on a little bit of elementary mathematics that says that if you got a number that factors into prime numbers, that factorization is unique, except up to ordering. So that, no 2 people are sent to the same number. Now, this is going to leave some rooms open. Room 14 isn't going to get anybody in it, but that's fine. we've kind of shown how to tuck these guys, sprinkle them into infinitely many rooms along the way. You can go more with this, right? We could say infinitely many ferry boats show up on the Hocking River. Each of them has infinitely many, infinitely big party buses. Do the same sort of game, except you would maybe use 3 numbers here to sprinkle them in. So, I mean, what I'm getting at here is infinity is big, and it doesn't behave like finite stuff does. And it kind of, I guess one of the ancient postulates handed down from the Greeks is that the whole is greater than the part. Well, this clearly violates this because we've got, sub-collections of the natural numbers are clearly just as big as the whole thing. So mathematicians there take that usually as maybe a definition of what it means to be infinite, is that you can do this, you have the same size as one of your sub-collections. Finite numbers don't have that property. I'll give you a definition here. Let's say that a collection of objects, people, is countable if it's possible to accommodate them all inside the Hilbert Hotel. Okay? Let's take that as a definition. The numbers 1, 2, 3, 4, 5, 6, you can think of those as a collection of objects. That's countable because you send the number n into room number n, and that fills up the hotel. Really what's going on when I say countable is that a collection is countable essentially if there's a bijection with a subset of the natural numbers, but I'm kind of sweeping all that mathematics under the table and sticking with this hotel image because it makes sense given a collection. Can we figure out a way to house them all inside? Start asking some questions now. You okay with the definition of countable? Countable, when I say that, can I stick them inside the Hilbert Hotel and make sure that everybody is accommodated? So let's start talking about some mathematical objects here. Z, they're the integers. That's 0, -1, -2, that side, 1, 2, 3 off that side. Is that countable?
Yes.
Why?
Because you can put all those people into groups and you would still, like by shifting the numbers, people would still be able to.
Yeah. It's pretty much like when if 2 infinite party buses showed up, or actually maybe 1, right? I mean, kind of you got the Hilbert Hotel filled with these guys, and suddenly these infinitely many people show up. Well, we can still stick them inside the hotel by shifting, right? So that's countable. Get a little more difficult here. Q plus. These are the positive rational numbers. And what I mean here, these are just your numbers that can be expressed as fractions of integers. So 4 is a positive rational, it's 4 over 1, but so is 3/8, 49, 50-seconds. Anything that can be represented as a fraction. There are clearly a lot more of these than there are these, right? Well, than those, if we're dealing with the positive stuff. This guy, is it countable or not? Can we stick these guys inside the Hilbert Hotel in such a way that everybody's accommodated? I hear some yeses. Are those supported by evidence or just guesses? Yes? You can think of it that way. I mean, it's kind of like we've already seen it's possible to accommodate. Yes, because he's thinking of having infinitely many corridors on infinitely many floors. And that's, we don't need to build up floors. We can kind of divide the infinitely many rooms into infinitely many infinite pieces and take care of it that way. The picture I want you to have is when the infinitely many infinite buses show up, how do we accommodate them? you can think about the fractions that have, I don't know, a 1 in the denominator. How many of those are there? There's 1 over 1, 2 over 1, 3 over 1, 4 over 1. That's countable, right? How about the ones that have 2 in the denominator? Well, 1 over 2, 2 over 2, etc. On up the line, you're going to be sure you're probably overcounting, right? 2 gets taken care of a couple of times. 4 divided by 2, 6 divided by 3, etc. But, that's okay. It really is just that same picture of when the infinitely many buses showed up. We weave them in. You could take the first, the fractions with 2 in the bottom and put them in rooms numbered by powers of 2 if you want. The ones with 3 in the bottom, put them in the rooms that are numbered by powers of 3. Those are disjoint. You can't be a power of 2 and a power of 3. Work your way on up the line. You need to do this with prime numbers. I guess the third group would be put in rooms that are multiples of 5, etc. So yeah, this is oddly enough not that bad. Maybe I'll share with you another little picture of how you might do this. This is very abstract art. That's going off the top. The top. So maybe you can think of the nth column is the nth bus, or the nth bus, and then these are the people seated on the bus, right? We've already argued that it's possible to weave these guys in, but it's also really easy to count them off, kind of going like 1, 2, 3, 4, 5, 6. You go to room 7, 8, 9, 10, going diagonal slashes, right? That's another way to view how you fit these infinitely many buses into the infinitely many slots. And then, again, back to the rationals, if you think of this column as being denominator 1, denominator 2, denominator 3, this gives you another way of seeing how all those fractions can be stuck in. I've got to deal with another case. In mathematics, we would write it this way. This is all real numbers between 0 and 1, including 0 and 1, right? So 1/2 falls into this collection, 1/3, 0 and 1 fall in there. But there's some funky numbers that aren't rational inside here, something like square root of 2 over 2, etc. Does anybody remember some, I guess this is probably middle school math. Maybe at my middle school, I don't know. There's some rational numbers tucked inside here, 1/2, 1/4, 3/4, etc. Do you remember how to identify the rational numbers inside of 0, 1, or just in general? Think in decimal expansions here. Do you know anything about decimal expansions and rational numbers and irrational numbers? Yeah. And so what we have here is the correct answer that if we've got a rational number is between 0 and 1. When you look at or just in general, when you look at their decimal expansions, they either terminate after finitely many things, like 1/2 is 0.5, or they repeat, like 2/3, 0.666666666 on down. And then that picks out the rational numbers here, but there are also some numbers that don't repeat. I can sit up here and I would be here a long time, but 0.1, 2, 5, 9, 3, 10, or whatever, keep going. That's a number that's between 0 and 1 that isn't rational. Its decimal expansion doesn't repeat. So this is a lot bigger than the rational numbers. The question I want to address is this countable? Can we tuck all these things into the Hilbert Hotel? Now, I will warn you that this is probably the most subtle mathematical point I will make in this talk. And it's something that even grad students get tripped up on sometimes. What I'm about to show you is a great trade secret in mathematics. maybe I can use a few volunteers from the front row here. So let's imagine that this is countable. There should be some way of housing every single number in this interval in one of the rooms of the Hilbert Hotel. So what I have here are a few random numbers between 0 and 1 that may or may not be rational. And we'll start over here. Here, you're room number 1, you are room number 2, you are room number 3, you're room number 4, 5, 6, 7. I have infinitely many cards left, but maybe I'll just stop. Oh, you can be 8. There you go. I will keep going down the line and handing out the rest of my infinitely many cards. So this is an attempt to take all the numbers between 0 and 1 and shove them into rooms. Okay? I've shown you what happened for the first 8. Use your imagination for the rest. So what I'm going to do is go down the line here, and I'm going to ask the person in room N what the nth digit of their card says. Okay? So, Matt, what does your first digit say? 5. What I'm going to do is take his 5 and add 1 to it. Okay, number 2.
9.
Second digit is 9. I'm going to add 1 to it and call that a 0. Yeah. And 7. Where are we, Oscar? 2. I'm going to add 1 to it. I'm going to put a 3 there. Kevin, 6 is going to be 7. Goes to 3. Goes to 3. 7, and I'm going to keep asking the infinitely many imaginary people I gave the infinitely many imaginary cards go. So you can see that what I've done is I've used my room assignment to generate a new number. Okay? Now, my wise audience, this number is between 0 and 1, right? Is it in room number 1? Why not? First digit's wrong. Is it in room number 2? Second digit's wrong. Is it room number 3? 4? Well, so it isn't in room 1, it isn't in 2, it isn't in 3, it isn't in room 4. I keep doing my imaginary stuff. It isn't in room 2,355,000 because I made sure that it disagreed with the guy that's in room 2,355,000 or whatever. So my question is this guy in a room? No. So that was my attempt to fill this hotel. I found somebody who was left off. Now you might say, okay, that's not a big deal. We've seen the Hilbert Hotel can swallow a new person, no problem. But this is a problem that you can never fix because no matter how I distribute those cards, that procedure I just gave you will give you a number that isn't in any of the rooms. Now, what do we conclude from that, right? Are the numbers between 0 and 1 countable or not? No. So, I mean, the deal is that you can't fit all the numbers between 0 and 1 into the Hilbert Hotel. There's always this weird diagonalization stuff going on. You can always, every list will fail. Now, having been an editor of a few journals in logic and set theory, I can tell you that this is probably the #1 generator of crank articles that you could ever imagine because this is a hard thing to swallow. People are like, can't you just fix it? And the point is, no matter how you try, you will always fail. This procedure, handing out the cards, room assignments, is always going to leave at least one person out. So that tells me that 0, 1 is uncountable. Now, what we can conclude from this is that there are at least 2 sizes of infinity when you deal with mathematics. Is that as bad as it gets? So I want you to imagine now another hotel. We'll call this one Cantor's Hotel. And to visualize the rooms as being 2-dimensional in a sense. So for every number between 0 and 1, there's a corresponding room. Okay? It doesn't line up in a list like the Hilbert Hotel. It's kind of, they're all crammed in, two-dimensional. But, you know, room numbers are fine. Huh? Sure.
What if you distribute infinite cards? So each card has one number. Are you going to have that left out number if you distribute infinite cards?
You're always going, so he's asking about, I guess, kind of the number infinities things we get, right?
Are you going to have one person left out, or
There will be infinitely many people left out if you do this procedure. It's never going to be just finitely many people left out, because we've seen the Hilbert Hotel can always swallow finitely many more people. So that's kind of the issue. Not only are there some things left out, there are a whole heck of a lot of things left out. But we don't need to know that we're uncountable. All we need to know is that there's always going to be at least one thing left out. Now, this particular hotel gives you a kind of another size of infinity. I will give you a little bit of terminology here. Go back to Sesame Street, they tell you what the number 3 means, and they tell you the symbol for 3. We've talked about countable, and we've got the idea that, you know, that is kind of an infinite number. Countability is an infinite number. It has a name. It's called Aleph 0. That's the number of objects in a countable collection. So anything that's countable, well, in an infinite. An infinite, I mean, anything that fits in the Hilbert Hotel exactly. We say it has size Aleph 0, okay? This, 0 to 1, has size, it's called denoted 2 to the Aleph 0. Now, I'm not going to torture you with the arithmetic of infinite numbers, but this is exponentiation redefined in an infinite setting. But this gives you a name for the size of this. And of course, what we've discovered is that Aleph 0 is less than 2 to the Aleph 0. So there are at least 2 different sorts of infinite sizes. I will tell you a trick here. If you have this vision of a hotel, the Cantor Hotel, set up over the interval from 0 to 1, you can get an even bigger infinity out of that. And the collection of objects you look at are the number of room assignments that are possible for the interval between 0 and 1. You know, every number gets into a room. How many ways can you do that? That will give you something even bigger. And of course, this trick is going to work with any of these hotel analogies. Given a collection, I can always, using this procedure, give you something that has larger size. So not only are there 2 different sizes of infinity, there are infinitely many sizes of infinity, whatever the heck that means. And it means more than you think. Again, I said this was my career choice. So, maybe belabor the point a little bit. We've talked about the interval from 0 to 1 and how it's uncountable, and declared that its size. What if I look at instead a square, side length 1, and all the points inside? So each edge of the square is a copy of the closed interval from 0 to 1. Does this fit in the Cantor Hotel? Is there a way of taking all these points and matching them up somehow with the numbers between 0 and 1? It's a little bit harder than the apples and oranges at the start, right? He said. But let me think about what is a number, what does a point in here look like? We know from basic algebra that it can be described with 2 numbers, kind of the x-coordinate and the y-coordinate, right? And each of those is a number between 0 and 1. So you can imagine the x-coordinate is 0.1235939, whatever. The y-coordinate is 0.75, whatever. I want you to imagine shuffling an infinite deck of cards and just kind of mixing those 2 infinite sequences together. Take one here, one here, one here, one here. kind of meld those together, what you end up with is an infinite sequence of numbers, right? And if you start with different sequences, what I'm getting at is this is actually a matching between the points in the square and the points on the bottom. So you can do the shuffling. And so that actually this has size to the L of 0 as well. Same, of course, would happen with a cube or multiple dimensional things. This is really the grown-up version of the party bus idea that we saw with the Hilbert Hotel. We're doing it now with, okay, now we really are in Halloween territory, I think. Maybe I want to take a few minutes, though, to tie this little discussion in with my own research. Okay, this is fine and interesting, but what do you do with it? Let me wave my hands here for a little bit. I want you to imagine the number line in front of you. Okay, so it has, the interval from 0 to 1, the interval from 1 to 2, etc., on out. That number line has the same size as this. I won't give you the argument, but it's not hard to see. And stuck inside that number line are the integers, 0, 1, negative 1. So we've got a picture that looks kind of like this. And in the course of our discussions, we've talked about various subsets of the number line. We talked about the integers and the rational numbers, and we decided that those guys were countable, right? And then we have this interval has size 2 to the L of 0, and the whole line has size 2 to the L of 0. The question maybe arises is, are those the only two things that can happen? If I give you some subset of this, is it either countable or is it of size 2 to the L of 0? Or is there some sizes in between that maybe we can't see? Okay, that's a reasonable question, right? This question has a long history. Hilbert of Hilbert Hotel fame gave a famous lecture at the dawn of the 20th century where he listed several problems that he thought would guide the development of mathematics for the next 100 years. That question I just asked about intermediate sizes was number 1 on his list. Cantor had a sad fate. In fact, set theory has a long history of people going insane. I wonder why. Cantor, part of the legend around Cantor is that one of the reasons he went mad is he couldn't answer that question about whether or not there were some infinite objects hidden inside the real line that were of size, they were uncountable, but still weren't as big as the whole thing. It turns out, and this is the pretty cool part, that this is a question that we can prove that we don't know the answer to it and won't know the answer to it. Now again, this is going to be, when I talk about this, I kind of get, mathematicians tar and feather me, but it's like postmodernism in mathematics. The deal is, our current conception of what mathematics is, based on thousands of years of cultural development, cannot decide whether or not there are intermediate sizes here. And what do I mean by that? Well, I'm a set theorist, and what set theorists study are sets. And what sets are, I guess you can think of they form a foundation for mathematics. We can write down a set of rules that kind of define what sets are, and then use those rules to generate a universe in which we do mathematics. So inside this universe, there's a copy of the natural numbers, there's a copy of the real line. Anything we want to do mathematics with is there. Okay? We can build different universes where all of mathematics as we know and love it holds, but the answer to the question I ask is different depending on which universe you're standing in. That is weird. It's not something that people are used to in mathematics, but I look at it as kind of well, let me ask you this, somebody in my audience. Do we know how to define what a unicorn is? If I ask you what is a unicorn, what would you tell me? Horse with a horn, and maybe magic? Okay. You agree that this is a reasonable definition of unicorn, right? Okay. Does a unicorn have a pituitary gland? It depends, right? I mean, do you cut them? Are they gooey marshmallow inside? Are they, real functioning biological beings? This is kind of the same situation we have here with the answer to that question. It's that we have some ideas about what mathematics is about, but there's still some things we can ask that aren't decided by the rules we laid down. And that's kind of what my research is on, is I go through and look at standard mathematical questions that haven't been answered, and sometimes I can show that, well, they can't be answered based on our current conception of mathematics. It's like we're finding holes in the logic of mathematics. And you get used to this. Some people, some mathematicians like throw up their arms and turn their backs and saying, whoa, dude, we're asking the wrong question, stay away. Others embrace this kind of ambiguity. But I guess I'm treading on the topics for another lecture at this point. So maybe I'll stop. Yeah. So he's saying, it's asking about what are we doing? Are we proving a negative? What we're doing here is building two universes. Okay? So a mathematician standing in each universe would have, recognize everything. Oh, this is my mathematical furniture. But somewhere in the attic, there's a difference. And this difference doesn't have, I guess, anything to do with addition, subtraction, all the standard mathematics. So what I'm saying is we are proving that we can't prove something by demonstrating that there are places where all our axioms defining mathematics are true, but where the answer to this question is different. And that tells us, if we believe in the power of logic, that the answer to this question cannot be derived based on the axioms that were true. I don't know if... Yeah. Okay. Is there an absolute zero? Well, if you're a set theorist, there is, because what we start with as a set theorist is a collection that has nothing in it. We call it the empty set. Well, in what sense do you mean absolute zero? Let me see. Okay, she's asking if there's some sort of absolute zero floating around there. My answer to that would be yes, in that mathematicians who are taking set theory as a basis for their mathematics have at their disposal a collection with nothing in it. And we can talk about the size of that collection and define that to be zero. And then the way we build the natural numbers out of that would be to take that collection with nothing in it and make a collection that has that collection in it. So if you think about the empty set as an empty purse, we can get another purse with an empty purse inside of it and call that number one and build things out of nothing. So there is kind of a zero that makes sense between all of these different possible universes of mathematics. Yes?
Your initial example where you had two apples,
Yeah.
two oranges to start with, we're told in early graduate school that you can't compare.
Well, I just turned your education on its head, didn't I?
To extend the idea, are there sets that it's not logically, we're not logically able to compare?
Okay, so he's asking if there's sets about which we can't logically compare. So I described in answering the question about zero a situation where we started with an empty bag, and then from that and the ability to stick things in other things, we built up a universe. You can also start a universe with this empty bag and also, 43 cows. And build a universe out of everything, sticking cows in purses and stuff like that. Now what happens there is that kind of at the ground level of the universe, where we start everything off, there are some things that are not really comparable. They're different, but we can't really say why they're different. This is getting on some difficult philosophical ground. I don't want you to have nightmares. Yeah, over here. Yeah.
So earlier you said
He was asking if there are possibly an infinite number of universes, and the answer to that is yes. The techniques of set theory allow us to construct mathematical universes with all sorts of properties, and we use them to detect whether or not something might or might not have a proof. Oh, there. Exactly. Okay, so he's asking some serious math here about Kurt Gödel and the incompleteness theorem. It's true that when I said that this question about sizes, about whether everything in the real line is either countable or has full size, when I said that that was independent of things, that's a hole in mathematics. Gödel proved that any reasonable way of writing down what mathematics is going to have a hole in it. And I guess an easy way to do it, he found, I always think about this in terms of computer science, right? When you write a computer program, really what you're generating is a sequence of binary symbols. So he figured out how to make sequences of symbols talk about themselves. And so what he was able to do is write down a sentence that says, I am not provable. And then you ask yourself, well, is that sentence provable? Well, no, because it would have to be true, but then it would contradict itself, because you can't prove something that says it's not provable without it being false. And there's a vice versa thing as well. Yeah. Oh, Fraley, okay. He's one of my ex-students, so.
Just to clarify, set theorists, they're trying to study things that cannot be solved because the current laws of mathematics that we know right now say that they cannot be solved. It's different, which is different than just saying, like, we just don't know the rule for this yet.
Exactly right. So he's giving a good description of what set theory is about. We're not just saying, I don't know the answer. We're saying that not only, we know that we can't know the answer based on the current rules for mathematics. So, I mean, that is a much stronger thing. Okay? Okay, yeah. Okay? Okay. Exactly right. So this is probably one of the most popular math questions on the internet, actually. We get into argument. I mean, she's asking about repeating decimals. So getting away from the 9, right? Why is 0.999999999 the same as 1? It seems like, well, isn't 1 like infinitely smaller than the other somehow? Again, when you do this, solve it algebraically, you come out to be equal. The way I think about this, and I try and explain it, is if 0.9999999 whatever was less than 1, there'd have to be some distance between it and 1. And you could take the average of those two things and find something in between. What would that look like? It can't be anything, right? So that means that there isn't any room between 0.999 and 1, so geometrically they have to be the same. And the way I always think of it is like it's just having a nickname. I mean, there's nothing wrong with, but you learn about this stuff in Calc 2 when you talk about infinite series. So we had one over here. Yeah. Well, that's a very good question. So he's asking about comparing the size of the interval from between 0 and 1 with the size between 0 and 100. And what we can do is think about the hotel image as well and say, you know, what room I'm going to put you in, pick a number between 1 and 100, divide it by 10. And that's your room assignment. That will fill up exactly Cantor's hotel. And the point is dividing by 10 gives you a function that, you know, you don't get any repeat values. It will scrunch that interval between 0 and 100 down to the interval between 0 and 1. So anything that you can do by putting your hands like this on the real line is going to have the same size as the entire thing. Yeah, sure.
We have a number, let's say, if we keep on dividing in times, will we get 0?
Well, this is using infinity maybe in a different sense. This is, huh? Oh yeah. He's asking if we have a number and we divide something by infinitely many times, do we get to 0? That's thinking about infinity as kind of a process. that we're doing infinitely many steps, as opposed to just having an infinite collection there. So the answer there would depend on what you're dividing. I mean, you divide something by 1/10 over and over again, it keeps getting bigger and bigger and bigger and bigger, right? Something, am I right? Dividing by 1/10, multiply by 10? Right. Wow. Yeah.
I was thinking about the Euclidean geometry.
Okay.
Coming out of your set theory,
Okay.
and in Euclidean geometry, there are typically 5 Euclidean postulates.
That's right.
But if we leave off the 5th one,
Mm-hmm.
the system is still consistent.
That's right.
And you can prove just about everything.
That's right.
In that system, if you change the 5th postulate, parallel lines don't meet.
They do.
They do meet in 2 places. You get spherical geometry.
That's right.
And I'm wondering if with the 2 answers to your question, do you get practical things like spherical geometry, which works for navigating on the Earth, plane geometry, which works like for navigating this room? You get similar kinds of useful mathematics with the 2 answers to set theory.
Wait a minute, you just said useful. I want nothing. I want no truck with that. No, but he brings up a. Shh. I don't want to get a real job. So he brought up an interesting, an exact parallel. I'll use the word parallel, right? With non-Euclidean geometry, you can leave off the 5th postulate, the parallel postulate, and change it. And you get different types of geometry that are useful in describing different physical situations. That's exactly the same analogy that we have with the different answers to the question about intermediate sizes. You're changing, you can take it or you cannot. So the deal is, the answer is yes, but it depends on what you perceive as useful. Okay? There are situations where you can assume one of those 2 answers. So assume there are no intermediate sizes. That's something called the continuum hypothesis. That assumption turns out to have a lot of power in mathematics, that you can solve some questions using the continuum hypothesis that can't be solved otherwise. Now, this is not going to help me solve a differential equation or something, but this does have a footprint in pure mathematics, topology, algebra, analysis. This kind of stuff comes in all the time.
Be able to identify the world you're in.
Yeah, well,
Based on what you see from that assumption back. Like you could maybe decide if you're on a sphere or on a plane.
so
Like triangles, angles on triangles.
So yeah, this is something we can talk about, the geometry of the universe. What kind, is it Euclidean or non-Euclidean? In theory, if you could measure things exactly, you could look at, take the angles of a triangle and see if it adds up to 180 or less or not, to tell you about the structure of the universe. You can do something similar to that in set theory, but it doesn't have a physical footprint. People, you'll see some articles in physics, maybe, I don't know how reputable the journals are, about, we can have some physical experiment that will figure out the answer to this question. And then it gets the philosophers excited, but the mathematicians are like, yeah, right. That's kind of, so yeah, that's kind of, in theory, yes.